This video is a tutorial on drawing motion maps. In it, we'll discuss positions, instantaneous velocity vectors, and acceleration vectors. Here are the initial conditions for our example. To follow along easily, I've color-coded the position, velocity, and accelerations. We'll start with a grid. You're welcome to use graph paper or ruler to draw your motion map. I've taken the time to solve for the position and velocity at clock readings 0 through 5. We'll use this as reference to confirm our drawing of the motion map. I've noticed that the position ranges from negative 5.5 meters to 8 meters. We'll go ahead and note that on our number line. We can jump right in and show that at 0 clock reading, the position is 2 meters. We'll go ahead and draw our velocity vector in for that of 6 meters per second. Notice I've drawn this at a half scale compared to the position. I've drawn it from 2 meters to 5 meters. We'll go ahead and add on our acceleration vector. We'll draw this at half scale also. Notice it's in the opposite direction. I've also placed it with the tail of the acceleration at the head of the velocity. We know that 6 plus negative 3 is positive 3. This black vector will be used as a tool to move around and find position and velocities. Let's talk a little bit about the vector addition. I'll drop everything except the vectors. 6 minus 3 is positive 3, but the units should concern you a little bit. Can we really add 6 meters per second to negative 3 meters per second? We'll drop the numbers and just talk about the symbols a little bit. That acceleration for us is for the time interval of 1 second. If we go ahead and manipulate that a little bit, we can actually show that it can be delta v. The change in velocity is equal to acceleration times the change in time. The change in velocity and acceleration are numerically equal. And we can see that v at 0 plus delta v equals v at time 1. It may look like we're going in circles, but students should take the time to have it make connections for themselves. If we look at it algebraically, and we say the starting velocity plus the acceleration times the time interval equals the velocity at 1 second. Through some algebra, we can find that the acceleration equals the change in velocity or the change in time. This is consistent with the slope of our velocity time graph. Let's go back to our story. We have this black vector sitting there, and what we're going to do is we're going to move it right to the end of the velocity vector. And we'll take that 6 meters per second and that 3 meters per second. We'll actually note that we have a new position, and that new position is at 6.5 meters. Students should take the time to find out why. Why does it work that I can add the half scale 6 meters per second and the half scale 3 meters per second and get the new position of 6.5 meters? This black vector is going to be moved one more time, and it actually represents our velocity vector at the 1 second clock reading. We'll continue this pattern and show that we can add the acceleration again, and we notice that 3 plus negative 3 is 0. That black vector that was there before is no longer there because it's worth 0. So we'll put it on the end of our 3 meters per second, and 3 plus 0 is 3. So our next position is at 8 meters. Since we go ahead and use that black vector to represent our next velocity, well, it's 0. So our velocity is 0 at the clock reading 2 seconds. For ease, we'll go ahead and move that up. It's still at 8 meters. We'll continue with the pattern and add on our acceleration. We'll go ahead and check it. 0 plus negative 3 is negative 3. That black vector gets moved to the end of that velocity vector, which was 0, and our new position is at 6.5 meters. Well, we still have to use that black vector as our tool, and we'll put it on the other side. And guess what it represents? It represents the negative 3 meters per second at clock reading 3 seconds. We'll go ahead and add the acceleration again of negative 3. Negative 3 plus negative 3 is negative 6. And remember, we'll move that to the end of that velocity vector and show our new position is 2 meters. Well, that black vector has another use, and it will show our new velocity at 4 seconds is negative 6 meters per second. We'll continue this pattern, and we'll keep adding on that negative 3 acceleration until we are done with our motion map. This is a completed motion map. It shows the positions, the velocity vectors, which are changing, and the acceleration vectors, which are uniform in direction and size. So to recap, a motion map will show our position at each clock reading, our half-scaled instantaneous velocity for each clock reading, and our half-scaled acceleration vectors for each clock reading.